Hey everyone, and welcome. Today, we're going to bend our minds a little. We're going to take something we all think we understand, computation, and look at it through three very strange and kind of wonderful new mirrors.
All right, let's just jump right in. I want you to pause for a second and really ask yourself, what is a computation? No, seriously, what is it at its absolute fundamental core?
You know, the immediate answer for most of us is, well, it's like a recipe, right? A sequence of steps, a process you follow. But what if that's just one way of looking at it? What if that's just one reflection of a much deeper, much weirder reality? Today, we're going to step into this, I guess you could call it a conceptual funhouse, and we're going to see computation reflected in three totally different mirrors. Each one is going to distort the image, sure, but each one also reveals something truly profound.
Okay, so here's our first stop. I call this one the giant lookup table. Now, this first mirror is wild because it completely, totally ignores the process. It doesn't care how you get the answer, it only cares about what the answer is.
The key idea here has a fancy name, extensional equivalence. But don't let that scare you. All it really means is that if two different programs, two different algorithms, always spit out the same exact output for the same exact input, then they're basically the same thing. It doesn't matter if one is some crazy, super complex neural network and the other is just a dead simple list. The journey inside the black box? Totally irrelevant. All that matters is the destination, the final result.
And this slide really nails the concept. On the left, you've got your standard algorithm, right? Take an input, do step A, do step B, get an output. Familiar stuff. But from this extensional point of view, for any set of inputs you can actually run, it's exactly the same as the thing on the right. Just a simple table. Input X goes in, output Y comes out. Boom, that's it. All those complicated steps in the middle, poof, they just vanish from this perspective. And get this isn't just some abstract thought experiment, because any computer we can actually build in the real world has finite memory. This applies to, well, everything. That massive neural network you're training? From this viewpoint, it's just a giant lookup table. The incredibly complex logic inside your laptop CPU? Yep, a lookup table. A countable Markov chain? You guessed it, it's just another lookup table. It is a shockingly, almost absurdly universal idea.
And all this leads to a pretty stunning formal result, which is that every deterministic, implementable algorithm is extensionally equivalent to a lookup table. I mean, let that sink in. It might be a static table so enormous we could never write it down, but fundamentally, it's just a table. All right, you ready to move on? Let's go to our second mirror. We're going to shift gears here, moving from that completely static, frozen view to something dynamic, but dynamic in the absolute simplest way you can imagine. Welcome to the universal shuffle. So, what if I told you that every single computation, I'm talking everything from calculating pi to the billionth digit to running the most complex video game, what if all of that could be done with just one single action? Not a long sequence of steps, just one. Okay, so this wild idea is called the permutation model. Here's the recipe. Step 1, you take your input data and you encode it not in the values of the bits like 1 or 0, but in their physical arrangement along a ridiculously long string of bits. Step 2, you apply one single, perfectly chosen permutation, basically a shuffle, to all the positions of those bits. Just one shuffle, that's it. And then step 3, you just read off or decode the result from the new arrangement. The entire computation is the shuffle.
So the absolute key here, as the source material says, is that the information, the data, the computation, it's all encoded into the arrangement of things. Imagine you have a fixed number of ones and zeros, and your whole job is just to move them to the correct final spots. It's kind of like solving a Rubik's Cube with one single, perfect, pre-calculated twist.
So when you look through this mirror, universal computation has nothing to do with logic gates or step-by-step operations. It's just shuffling. A single, massive, almost cosmic rearrangement of things. It's just such a beautifully simple, minimalist way to think about it. All right, deep breath. Let's turn to our third and final mirror. And I gotta warn you, this one is probably the most abstract, the most mind-bending of them all. We're leaving the idea of process completely behind. Here, we're going to view computation as pure static structure. This mirror really forces us to confront a fundamental question. When you think of a simple function, say add 1, do you picture it as a little machine, a process that takes a number and transforms it? Or is the function itself a single, static thing that just exists all at once? Okay, so here's where it gets really wild. Mathematically, you can think of a function, say from A to B, as a section. Imagine a space of all possible input-output pairs. The function is just a very specific slice through that space. It's not a verb, an action, it's a noun, an object. It's like this timeless, geometric shape that already contains all the connections between every single input and its one true output.
And the implication here is just, wow, the function is the shape. The computation doesn't happen over time, it just is. The entire map of every input to every output already exists as this complete whole thing. When we compute something, all we're really doing is just tracing a path along a structure that was already there.
There's another cool way to think about this, and it comes from a pretty high-level field called category theory. But the idea is simple. Imagine you have a bunch of data that's organized or indexed by one set of labels. A function is basically a tool that lets you reorganize or reindex that same data using a different set of labels. So think about that. Computation isn't about creating something brand new. It's just about translating information from one perspective to another. It's like looking at the exact same object, but through a different window.
Okay, so let's step back from this crazy funhouse of mirrors for a second. Let's try to pull all these reflections together with one final, kind of cosmic perspective.
So, we've seen computation as a giant, static lookup table. We've seen it as a single, universal shuffle. And we've seen it as a timeless, geometric object. I mean, three totally different, you could even say contradictory ways of looking at things. And yet, each one is a perfectly valid reflection of the same fundamental reality.
But here's where we get to the final, mind-blowing twist. Picture the space of all possible problems you could ever even think of. Now, what's the probability that if you picked one completely at random, it would actually be solvable by a computer? The answer, mathematically, is 0. The solvable problems, the things our computers can actually do, are like a few grains of sand on an infinite beach. They exist, but they are infinitely rare.
But then, you look at the physical world we actually live in. There's this thing called the Poincare recurrence theorem, and it basically says that any system with finite boundaries, and that includes our computers, maybe even our universe, must eventually return to a state it has been in before. Not just once, but infinitely many times. So in the real, physical world, patterns and repetition aren't just likely, they are absolutely 100% inevitable. And that leaves us with this incredible paradox, doesn't it? On one hand, in the pure abstract world of ideas, solvable problems are infinitely rare. But on the other hand, in the physical world we inhabit, patterns and repetition are completely guaranteed. So if the answers are so incredibly rare, but the patterns are literally everywhere, where should we even be looking? Now that is something to chew on.